All right, it is 9 a.m., so we will get started with our virtual field trip for this morning. Welcome, fourth graders, to the second week of school, and welcome to the Dallas Independent School District STEM Environmental Education Center. We've got 4 schools with us this morning. The first one is Kaye Tigers. Welcome. And then we've got Hotchkiss Elementary with us this morning, so welcome, Hotchkiss Elementary. Some students from Granbury ISD, welcome. And some students from the Dallas Academy. We're very excited to have you with us today. And thank you for registering for this field trip. If you have not registered for this field trip yet and you're watching this, you can do so by going to www.tiny.cc/EEC register, and you can get yourself or your class registered for this morning's field trip. This morning's field trip is going to explore physical properties of matter. And during this field trip, students will discover that matter has measurable physical properties, and those properties determine how matter is classified, changed, and used. Some of the physical properties we're going to explore this morning are temperature, classifying matter as a solid, liquid, or gas, matter's ability to sink or float, and whether or not some matter is attracted to a magnet. And while we explore these physical properties, we're going to be using some tools. The tools that you're going to see this morning are a thermometer, a beaker, a pan balance, a triple beam balance, and a magnet. Now, while you're watching these investigations, you can ask us questions, but how you do that on a virtual field trip is by going to www.tiny.cc/EEC-question-answer and ask us any question you'd like about these investigations, and we will do our best to answer them. You can ask as many questions as you like, and we'll try to get through all of them during these 45 minutes. So without any further ado, I'm going to stop sharing my screen here and turn it over to our first teacher, who is Mr. Monroe, and he's going to cover the property of magnet.
Good morning, good morning. Good old Monday morning. Well, students, before we get into our investigation using a magnet, I want to refresh your memory about what matter is. And it's very simple. Matter is something that takes up space. And you know, when we talk about the properties of matter, we're talking about how an object looks, feels, or acts. With the part of the virtual field trip that I'm doing with you today, basically what we're going to be observing is how certain matter reacts, or how it acts under the influence of a tool that we're going to use called a magnet. And before I get started on our investigation, also I would like to tell you a little bit about a magnet, because most people don't understand how a magnet acts or reacts, okay? And you know, thinking about history, you know, great things have always had somebody that has discovered them. Well, with the magnet, nobody can really claim to be the discoverer or the inventor of a magnet. Although there are a lot of stories and folk tales about how the magnet was discovered. I'm thinking of one that originated in the country of Turkey, where a shepherd boy was out trying to rescue an injured lamb, and he had a pair of sandals on that had nails in it, and his sandals got stuck to a piece of rock. Well, the amazing thing is that piece of rock is a type of magnetite, and the very simplest form of magnetite in its natural form is a rock called lodestone. And that's what magnets are made out of. This rock, this lodestone, has the ability to act as a magnet. You know, magnets are an object that can pull things, okay? And if there's 2 magnets, for some reason, if they're not turned the correct direction, they push away from each other. The secret is magnets have 2 poles. Some of the most common forms or shapes of magnets I want to show you though. I'm going to start out by showing you a horseshoe magnet. This horseshoe magnet is pretty good size, and on one side of the horseshoe there's an S, and on the other side there's an N. Another common shape for a magnet would be the bar magnet. And by the same token, I don't know whether you can see this, But on this end, there's an S. On this end, there's an N. Another common form would be a ring magnet. Now, I don't see an S or an N, but I'm sure that one side of this is an S and the other side probably is an N. And what those letters stand for, the N stands for North Pole, the S stands for South Pole. I know that you all have heard those terms before, and I think when you've heard them before, it's always been related to our planet, the planet Earth. You see, at the top part of our planet, we often call that area up there the North Pole. At the bottom part of our planet, we refer to that, or we call that the South Pole. So one could say that maybe our planet is just a great big magnet. How true? I don't know. In fact, I will say most likely that is true, okay? Now, the really strange thing about it is that if you have a magnet and you put it together to where it's going to either attract or repel, and when we use those two terms, attract means pull together, repel means push apart, okay? So I've got two small bar magnets here. There's an N on this end and an S on this end. So let's see, I'm going to take the two ends, these ends here, I'm going to try to push them together. And I can see they will not go together because they are repelling each other. The magnetic force is a force of repelling. Repelling means to push away, okay? Now, if I change this around and I take the S and I put the S next to the N, they are drawn together, just like that. Now, also, I want you to think about this. Here I have two ring magnets on a shaft. These two are pulling together. But if I put this one on, it doesn't quite go down, does it? It bounces. It will not go down and attract itself to the other one. Think about that. What do you think? You think maybe this might be the S pole, and on the underside of this ring is the S pole also, so what they're doing, they are repelling each other. But if I turn it around, and maybe this is the N and that's the S, look what happens. Wow. You know, magnets, they attract different types of matter. And I'm going to run a little test right quick using one of these bar magnets, and I'm going to put some items in a petri dish. I'm going to put a screw, some staples, paper clips, and I'm going to see if these objects that are made up of matter are attracted to this bar magnet. Wow, see that? And what that tells me, students, is that the items that are attracted to this bar magnet, evidently, they have some iron in their makeup. Part of their matter, which makes up the object, is made of iron. They are attracted to the metal. Okay? I'm also going to try another little test. I'm going to put another piece of metal, and I'm going to put a brad, which has a little different color. I don't know what it's made out of. And I'm going to put a plastic paper clip, and I'm also going to put a penny. And just for my own curiosity, I'm going to put a dime. Now, I'm going to take that same bar magnet. Whoa, won't pick up anything except the brad. Now, that's kind of strange, because I assume because this brad was a goldish color that maybe it didn't have iron in it. But evidently, it does. A penny, I know, is made out of copper. The other piece of metal in there is a metal called lead. And we know that a plastic paper clip is made out of plastic. So there are certain things that are made of certain matter that will not respond to the attraction of a magnet. You know, I can remember, I guess I should have remembered this, but when I was in the 4th grade, not too far from my house was a salvage yard. And what I mean by a salvage yard, a junk yard. People threw away all kinds of metal things. And they always ended up in this salvage yard. Refrigerators, old stoves, even wrecked cars. And I noticed that there was a crane in the middle of this salvage yard. And on that crane was a large magnet suspended in the air that they would bring down and pick up different metal parts. And I'm sure they were using that magnet to separate certain metals. See, that's one common use that they use a magnet for today. Another common use is this. You know, you ever get lost, like on an adventure in the wilderness or in the mountains, hiking along and you lose your direction? Most people carry an instrument called a compass. And that compass will give you the directions that you are moving unless it's influenced by some force. This is a model of a compass. As you can see, it has an arrow that's pointing toward the north and a south. Basically, I can tell you this compass right here is a real compass that I'm using. And if I lay it flat and I look at it, it's going to tell me what direction is north. Because that needle that's inside the compass is magnetic. And I can tell you, this classroom, my lab that I'm in, I know what direction north is. And guess what? The needle is pointing that direction. So that is north. You know, you can try this at home maybe if you have a bar magnet. But I made a homemade compass right here. And what I did, I took a ruler, I suspended it on a high tower, and I tied a string to the middle of the bar magnet. And I'm going to stop this from swinging. And we're going to see if this will give us the direction of north. I see that it's moving. Going back that way. Going back that way. Now it's going to go back a little bit more. Little bit more. And guess what? It's working its way to the north. That is north over there. Eventually it will get there. Now, students, hopefully I've given you a little information about the use of a magnet and how a magnet works. And they are also used in a lot of other equipment, electrical equipment. And one of these days, you'll study that and you'll find out they are very common and they're used in our everyday lives, not just for use as a compass or something to separate metal. Hopefully, you've gained a little more information about magnets. And now I'm going to turn it back over to Mr. Broughton, who should be able to answer some of your questions if you have them. Thank you for your time.
Thank you, Mr. Monroe. And we did have one question, which is, what are all the metals that are attracted to a magnet? And there are 3 common metals that are attracted to a magnet. Iron is one. You heard Mr. Monroe mention that one. Nickel is another one. And cobalt is the 3rd common metal that's attracted to a magnet. There are some more rare earth metals that are also magnetic, but the 3 that you're going to find most commonly are iron, nickel, and cobalt. All right, we're going to move on to our next property, which is temperature with Mrs. Fuller.
Good morning. Welcome to the Environmental Education Center. In this segment, we're going to talk about temperature. Temperature is how hot or how cold something is. And the science tool that we use to measure temperature is a thermometer. Now, this is a classroom thermometer. You probably have seen it. They're very common all across the district. And we've got 2 columns of numbers. These are scales. There are 2 different scales. On this side, it says degrees C, which is degrees Celsius. and on the other side is degrees Fahrenheit. Now, Mr. Fahrenheit, his name was Daniel, he invented the modern thermometer, and he also invented the Fahrenheit scale to read the thermometer. So if you'll look in the center of the thermometer, you'll see a long column, a tall glass column with a bulb at the bottom, and there's a red liquid, which is alcohol, in here. And when it gets warm, the alcohol expands and rises in the column, and then you look to either side to determine what the temperature is. So when Mr. Fahrenheit, Daniel Fahrenheit, invented the modern thermometer back at about 1709, he invented this scale so that people could read it, and it's a little unwieldy in comparison to the Celsius scale. On this scale, the Fahrenheit scale, freezing of water and the melting of ice both occur at 32 degrees Fahrenheit. The boiling of water occurs at 212 degrees Fahrenheit, and the average temperature of the human body is 98.6 degrees Fahrenheit. Well, a few years after he invented this particular type of thermometer, about 5 years later, in 1714, he substituted mercury for the alcohol in the column, because mercury is a metal and it's liquid at room temperature and is very, very sensitive to temperature change. It expands very quickly to temperature change. So it really made a more accurate thermometer. So we used that type until about the end of the 20th century. But the problem is the column in the middle is a glass tube. Mercury is poisonous, and if a thermometer accidentally is broken, it releases the mercury into the room. So we've gotten away from using mercury thermometers simply because of the poisonous nature of the mercury. Now, on the other side, on the Celsius side, Anders Celsius came up with a scale that was easier to read than the Fahrenheit scale. On the Celsius scale, 0 degrees is the freezing of water, 100 degrees is the boiling of water, and the human body's average temperature is 37 degrees. Celsius scale is what we use in the metric system. Fahrenheit scale is what we use in the imperial measurement system. Now, we have all different kinds of things that we measure. A lot of what we deal with in life has to have a precise temperature. So let's look at some of those different types of thermometers. So we're going to start off with a soil thermometer. Just let you see the scale on this. And you stick this in the ground. You're not supposed to plant your seeds or your plants until the soil is between 65 to 75 degrees. So this makes a handy tool to determine if the soil in your garden is the right temperature, so you'll have a successful garden. Now, this particular one with the long probe is a compost heap thermometer. You see that green area? That green area is the range that you want your compost heap to stay that temperature. If it gets below 80 degrees, there won't be any decomposition going on. It's too cold. And if it's above 160 degrees, it kills all the microorganisms. So you want to keep your compost heap between 80 degrees and 160 degrees, and you take its temperature, and if it's too hot, you add some water, and if it's too cold, you stir it up and try to get that action going in there. Now, this is a thermometer used for people, and I bet you've had your temperature taken quite a bit since March, because we're all very focused on not having fevers now. We've got, here's one right here. This is a thermometer we use. We do a lot of limnology studies here. We use this thermometer to measure the temperature of the lake. If you'll look at the top of this, you'll see that ring up there. We stick a really long string in it and fling it into the lake and haul it back and read it to see what the temperature of the lake is. Now, before we go on to our last set, I want to show you this thing. This is not a thermometer. It's what's called a thermoscope. It was invented by Galileo, very famous scientist, in 1593. And what it is a long column of water inside a glass tube, and he's got all these bubbles, these glass bubbles that have fluid in it, floating in here. To read it, you don't pay any attention to the ones that have sunk to the bottom. You look at the bubbles at the top. Each one has a tag at the bottom with a temperature. And so you look at the last tag that's still floating, and this one says 78 degrees. So my laboratory is 78 degrees. This particular thermoscope, thermo means heat, scope means to see, has a very small range. It's essentially good for measuring the temperature in a room. So it doesn't have heat extremes. All right, so we'll put the thermoscope back. Now, I want you to think about what's the hottest thing you can think of on the earth. Well, you might say, well, inside our oven, it's real hot. Well, that's true, it is. This is an oven thermometer to make sure your oven is very accurate. But there are some natural things that are much, much hotter than your oven. This is a picture of a volcano. Lava, when it comes out the top of a volcano, it's liquid rock. Its temperature is about 2,140 degrees. That's very hot. But look deep inside the earth, you'll see magma. Magma's even hotter. Magma has a temperature of about 2,400 degrees. So those are two things that are extremely hot here on our earth. We also have something in our solar system that is very hot, and that's the sun. The center of the sun, the core of the sun, has a temperature of about 27 million degrees. That is extremely hot. The photosphere has a temperature of about 10,000 degrees, and the chromosphere has a temperature of about 7,800. So even though different parts of the sun have different temperatures, they're all extremely hot. So this is a brief overview of temperature. We're going to turn it back to Mr. Broughton. He's going to answer any questions you have about temperature. Thank you so much. Have a good day.
Hello again. We did have one question, which is, how can water freeze and melt at 32 degrees Fahrenheit? And it freezes at 32 degrees Fahrenheit if it's liquid water and you're lowering the temperature. Once it hits 32 degrees Fahrenheit, it will freeze, but it will melt at 32 degrees Fahrenheit if you start with ice and then increase the temperature. So that freezing melting point is 32 degrees Fahrenheit, and it just depends on what you're starting with before you raise or lower the temperature. All right, we're going to move on to our next teacher, and we're going to explore states of matter. So take it away, Miss Nash.
Thank you. Welcome, fourth grade. Welcome to my classroom. Today we're going to be talking about states of matter. And there are three states of matter: solid, liquid, gas. And we define a solid as having a definite shape and volume. A liquid has a definite volume, but can change shape. And a gas, like the air that I'm moving through this balloon, takes the shape and the volume of the container. So that air took the shape of the balloon and the volume. Now, why are they so different? Let's put our fingers like this. We're going to compare them at the particle level, like this little picture right here. So put your hands up like this. You can imagine these are solid. The molecules in the solid are all just sitting there, standing there, stiff. They don't move. But if we add some heat, we might start to melt that solid. And then we're going to get a liquid in which the particles will move more freely. And then if we add more heat, that liquid might turn into a gas. And then the particles will just go everywhere, everywhere, everywhere. Give me more room, give me more room. Now, the only substance that we find commonly on our planet in all three states naturally is water. So we can have ice, a solid, and with some heat in this classroom, it's begun to melt. And then, as this bowl sat there, something began to happen on the outside. You see, there's condensation appearing. Water droplets on the outside. Is the glass leaking? No. Where did that water come from? That condensation came from the air. Because the air in the classroom actually has a lot of water vapor in it. Most of that water vapor came from evaporation. Do you see in that big word, a smaller word, vapor? And that just means the gas, the water vapor became a gas, a part of the mixture of gases that make up our air. Now, let's look at a liquid for a minute. Here. So I have 4 beakers here, and each one has the same amount of water, colored, 200 milliliters. Let's pour it in here and see a really interesting shape with that same volume. Okay. It's a big flat container. And the graduated cylinder. There we go. So if you just looked at these, you might not guess that they all actually had the same amount of liquid in them. The liquid just took the shape of the container. Now, gases are really weird because you can't see them. Sometimes you can smell them. So if you go with someone today, I know you're not driving, but someone else is filling up the gas tank in the car, and you're around that, you might smell that gasoline because it's a liquid that comes out of the pump, but it's really ready to become a gas, and you can smell that. That's what makes it so dangerous. Okay? It can explode. And so it becomes a gas really quickly. If you have a gas stove at home and you turn it on without lighting it, you can smell that gas. And again, they put something in that so you can smell it because it's really dangerous. But we don't often kind of realize that gas is particles. They're out there. It's matter. And it takes up space. So I put a balloon on top of my beaker here. And I'm going to try to get that balloon to go down in there. If I push it down in there with my finger, it comes right back up. If I try to blow it up in there, I just can't do it. And that's because the air in here, that mixture of gases that we call air, is pushing up against my finger and against the balloon. But sometimes a gas can change its state. And look at this. How did I get that balloon inside that beaker? Well, the beaker was full of air, but I tricked it. I put some steel wool in the bottom, and I put water in there. And then my steel wool began to rust. Can you see that rusty color there? Now, what rusting is oxidation. Do you hear that word, oxidation? Oxygen. So what happens as it rusts, the oxygen molecules in the air become a solid. And then instead of taking up a lot of room, they take up much less space. And so all that oxygen became a solid, iron oxide. And then when that happened, the balloon got pulled down inside. So pretty cool the way actually gas takes up space and takes. Now, around the house we find examples of our states of matter. Here's my Topo Chico, solid, liquid, and there's a little bit of air in here, so it's a little bit of gas, but there's more gas in there too. Because gases have a very unique property. Hear that sound? I'm opening it. Oh no. Whoops. Well, my Topo Chico was ready to get that gas in there. It's ready to get out. Look, see it? It's escaping. Let me out of here. Now, anybody know what that gas that's in there is? It's carbon dioxide, and it was in there under pressure because gases can be compressed. Okay, so they squeeze it on in there, and then when I shake it a little bit and then open it up, it wants to get out as quick as it can. If you have a Coke, or if I leave my Topo out overnight and I go to drink it, it's not going to taste right. What happened? Well, all that gas, all that carbon dioxide in there, so I chance, I'm getting out of here, and it escaped up into the air. Another place where we see those three properties in operation is our popcorn, everyone's favorite snack, right? It's just solid. Oh, I can squeeze it. Oh, it's hard. But if I put that popcorn in a pan and heat it up, what happened? I get popcorn. Wow, it exploded. Why? Well, because corn came from a plant, and plants, like animals, are a lot of water in them. Inside that popcorn was a little bit of water. And when it got really hot, it became water vapor, and it needed to get out like the Incredible Hulk, right? Pow! And then we have our yummy popcorn. So what I want you to do now is think about this. Now we said that liquids can be poured and they take the shape of their container. So what do you think about this? Is that a solid or liquid? Not a gas, obviously. Now it's pouring. It's sugar, actually, and it's taking the shape of the container. Does that mean it's a liquid? How could you figure that out? You might use your sense of touch to feel it. Okay, what do you think it feels like? You might take a hand lens and look at it with your hand lens, okay, to see if you can see something. So try this at home and see what you think. Is sugar a liquid because it pours and takes up the shape of the container, or is it a solid? Another thing I'd like you to do is go around your house, around the yard, the neighborhood, the schoolyard, the school, and find 3 things that are solids, 3 things that are liquid, and 3 things that are gas, okay, around the house. And then think about how those properties make them particularly useful. Okay. So I think that's all for me. If anyone has any questions, you can ask Mr. Broughton. Thank you.
Thank you, Ms. Nash. We did have one question, which is, how can a liquid become a solid or a gas? So I'm going to share a little graphic organizer that I think illustrates how a liquid can become a solid or a gas. So right here I have a liquid, and if that liquid is going to change to a solid or a gas, it has a lot to do with temperature. So if I increase the temperature for this liquid, it will evaporate and change into a gas. But if I were to decrease the temperature for this liquid, it would freeze and become a solid. So something can change state of matter usually by a temperature change. So if we just start from the beginning with a solid, if I increase the heat or the temperature for a solid, it will melt into a liquid. And then if I keep increasing that heat, it will evaporate and change into a gas. But then if I take away the heat, a gas will condense and change to a liquid. And if I keep taking away even more heat, a liquid will freeze and become a solid. So matter can change states, usually because of temperature changes. All right, we're going to move on to our final teacher, who is Ms. Ramirez, and she's going to talk about the ability of matter to sink or float.
Hello, fourth grade. My name is Ms. Ramirez, and in this segment, we're going to be learning about the property of matter called mass, and we're also going to learn about density. So to start off with, we're going to learn about mass. So mass is simply the amount of matter that is inside an object. And how do you think we can compare or measure mass? So probably in previous grades, you probably used a science tool that looks like this. This is called a balance. And we're going to use this simple balance to compare the masses of these two objects. So we have a little bead and then we have this wax candle. So if we're going to compare the amount of mass that these objects have, which one do you think might be lighter and which one do you think might be heavier and why? So I'm just going to put one object on either end and we're going to see what happens. So I'm going to put my bead in first and then my wax candle on the other end. So what did you guys see happen? So I noticed that the wax candle side went down. So what this tells us is the side that goes down is actually the heavier side. The bead went up. So the side that goes up, or the side that is higher, is actually the lighter side. So when we compare the masses of these two objects, we know that the candle has more mass than our bead. Now, today we're also going to look at another science tool used to measure mass, and that is a triple beam balance. So we're just going to go through a quick preview of how this tool works, and then we'll move on to sink and float. So here is a triple beam balance. I know it might be a little hard to read some of the numbers, but this is the triple beam balance, and the way it works, whatever you're measuring the mass of goes on top of the metal plate. So in this case, we're going to measure the mass of this box of iron pyrite. It's also known as fool's gold. It does look like gold because it's nice and shiny, but it's not real gold. So that's what we're going to be measuring the mass of. If we look at our triple beam balance, you'll see that there are 3 sliding bars with numbers. And then we also have a mark that says 0. And then we have this black arm with a white line. Your goal is to experiment moving these different weighted sliding bars until we can get this white line even with the 0 mark. And once you've done that, then you can read the mass that you have. So when you're experimenting with moving the sliding bars, you always start with the largest sliding bar first. This measures it in hundreds. Once you've gotten this down, you're going to move to the back and do your tens bar, and then you'll move to the front bar and you'll do the smallest bar last. So once you've got this to where that line is equal to the 0 mark, then I'm going to show you a close-up so you can sort of see how it's read. This is what the numbers look like up close on the triple beam balance. So this is the middle bar. It's the biggest bar, and it's the one that you're going to read first. So this one, in my example, is marked at 500 grams. So once you have this one read, you're going to move up to the back bar, the one that's in tens. This example reads it at 20. Once you have that one read, you're going to move up to the front sliding bar, and this one is in ones. So once you've read all 3 of these, you're just going to put the numbers together. In this case, we have 520. 3.2 grams. And mass can be measured in grams or kilograms. Now, the reason that we had to learn about mass today is because mass plays a role in our next topic, which is density. So density is simply how much matter there is in a certain volume. So that's why we had to learn about mass first. And you kind of touched about volume when Ms. Nash came and did her presentation. So to review, I know that's a lot of vocabulary words. So to review those 3 vocabulary words, we're going to look at an example. We have 2 boxes of iron pyrite again. How could you describe the mass of each box? Which one is heavier? Which one is lighter? How can you describe the volume of each box? And how can you describe the density of each box? So I know by holding these and feeling them that this box has more mass. It feels heavier. I can tell by looking at them that this box is more dense. It has more matter inside of it. And then I can tell by looking at them that these boxes have the same volume. So they both take up the same amount of space. So the volume of a box is simply found by multiplying the length times the width times the height. And that's how we get the volume of a box or a cube. So that's those three words. So now that we know what mass and volume are, we're going to learn how that relates to density. And density is important because it simply tells us if an object will sink or float. So to do our next experiment, we're going to look at a variety of different objects, and I'm going to have you make a prediction on which ones you think will sink and which ones you think will float and why. So the objects that we're going to test today, we have an empty Coke can, a piece of wood, a ping pong ball, the same wax candle from before, a bead, a pumice stone, and a limestone rock. So again, think about which one of those, if you need a reminder of what you saw today, think about the objects that y'all saw and make a prediction which ones will sink, which ones will float, and why do you think that way? We're going to move to the back table so that we can do our experiment. And the tool that we're going to use to do our experiment with is just a container filled with water. And I'm going to start with my big objects first, with our empty soda can and our piece of wood, and we'll see what happens. So right away, we notice that these two objects float. Did that surprise anyone? We also have our pumice stone. We have our ping pong ball, our wax candle, and then lastly, our bead and our limestone rock. So hopefully you guys were able to see that. The objects that float would be the Coke can, the piece of wood, the pumice stone, the candle, and the ping pong ball. So the reason that these objects float is because we can say that they are less dense than the water. So objects that are less dense than the fluid that they are in are going to float. The items that sank are the limestone rock and the bead. Did that surprise anybody? So what we can say for these objects is the objects that sink are more dense than the liquid that they are in. In this case, the rock and the bead are more dense than the water. So if y'all remember from our previous experiment, the bead and the candle, if y'all remember, the candle was actually more dense than the bead. But instead of sinking, the candle actually floated while the small, lighter bead sank. So think about why is that? So again, density takes into consideration an object's mass, but also its volume. So it's not just an object's size, or if it's heavy or light. There's other factors that play a role into whether something's going to sink or float. So it's really important that we test them to determine their density and their ability to sink or float. So really quick, we're just going to review a couple of vocabulary words, and then I have an at-home challenge for you guys to try and complete. So we learned that mass is simply the amount of matter that is in an object. You can use a simple balance to get a relative comparison of which object is heavier or lighter, or you can use a triple beam balance to get a measurement in terms of grams or kilograms. Density is simply the amount of matter or mass that is in a certain volume of a substance. So it can be found by mass divided by the volume will give you an object's density. So if we look at our diagram here, we have a lake. The boat and the water bottle are floating, so they are less dense than the water. The tire and our large rock sank because they are more dense than the water. And my at-home challenge for you guys today, see if you can create a boat that can carry at least 5 pennies and still float in a bathtub or a sink. And I also have a reflection question for you guys. Look at this container of water. Now, Imagine it's a container that doesn't have any of our items in there and it's just water. How could you find the mass of the water? And how can you find the volume of the water? My next question is, how can you find the mass of the container? And then how can you find the volume of the container? So see if you can answer those two questions. And that is all that I have for you guys today. We're going to give it back to Mr. Broughton, and he's going to answer any questions that you might have about mass and density.
All right, thank you, Mr. Ramirez. And we did have one question, which is, I saw an aluminum can float. Would an aluminum cube float in water? And I'm not going to answer that because you could probably figure that out on your own at home using some aluminum foil. If you put that foil in different shapes, like a can shape or a cube shape, or maybe like a ball shape, because it's hard to get some aluminum foil into the shape of a cube. You could probably figure that out yourself. So I'm going to let you explore that. I'm going to share my screen here so that we can review what we've done this morning. Let's see. There we go. So today, students discovered that matter has measurable physical properties, and those properties determine how matter is classified, changed, and used. We explored the properties of temperature, whether matter is a solid, liquid, or gas, matter's ability to sink or float, and matter's ability to be attracted to a magnet. And we did use a thermometer, a beaker, a pan balance, a triple beam balance, and a magnet. So thank you so much for joining us today. Please let us know how we did by going to www.tiny.cc/EEC feedback and giving us feedback on today's field trip. We care what you think and look forward to seeing that. So now I'm going to stop sharing my screen here and wish you a good rest of the day. Have a good day.